All right. So last week we talked about kind of the general underpinnings of what are tensors, the data types, and all of that kind of stuff. And in this chapter, we're looking at how do you actually take real world data, put it into tensors, and represent it as something that a neural network can utilize. And in the first section, we were looking at images. And so images is really one of the biggest areas that neural networks have really taken off and shown to be state of the art in. So I think it's a good example to start with that section because it's one of the more important regions. And so thinking about how we represent that numerically, an image, I think most people are familiar with like the different RGB values and pixel intensities and stuff like that. And so in PyTorch, what we do is we have an array, like we talked about last week, and the dimensions are channel by height by width. So if you think about that, that's red, green, blue. And then if your image is 300 pixels tall and 400 pixels wide, then that would be your three different axes, the shape of the image. And so there's a lot of different libraries that will load in images for you. There's OpenCV, there's PIL, there's Image.io, which they use, and they might load them in a different order than what PyTorch is expecting. So they might load height, width, channel instead. And so you need to know that sometimes you might have to swap that ordering. And so they showed there's a simple command where you can permute the axes and just kind of shuffle around. And the stuff we were learning about last week where you change the stride, you change the offset and all of that stuff. That's basically what permute is able to do for you, or change the underlying storage. One of the things they mentioned is if you're preparing a batch of images, it's better to generate one big array rather than a single image and then stack it with another image and then stack it with those two images and then stack it with the three images. It's just more efficient to make a batch and say, okay, my batch is going to be 32, so I'm going to make a 32 by channels, by height, by width array, and then place them all in that array. You can test that for yourself and see that it is actually a bit slower. You just time it and you can see that it's not really the way you want to go. And it gets worse as you add more and more images in a bigger array. One of the things they mentioned was that neural networks typically operate between 0 and 1 or -1 and 1, some bounded range. It kind of depends on what exactly your architecture is, what the assumptions are, but those are good defaults. And so images typically operate 0 to 255 across the red, green, blue channel. Each of those can have 0 to 255 intensities. And so in order to make it a format that's more presentable to a neural network, you typically want to divide by 255 is one way, or you can subtract the mean and divide by the standard deviation of all of the different channels. So if you're looking at the red channel specifically, you measure the mean across all of your images potentially, and then you divide by, you subtract that mean from the individual images, and then you divide by the standard deviation as well. And you can do that across the whole thing, or you can do that in batches, or you can do that through, there's different ways you can approach that, and they have various different pros and cons. Any questions in terms of the image section at this point?
This probably will have leaning into later questions as well. So it talked about doing the channel height and width versus, what I'm used to on image formats is how they talked about it being loaded, where it's like height, width, channel. Mm-hmm. Are there cases where, other than just like, hey, maybe I just want to look at the, the green channel for everything or the red channel for everything, versus like, why would you do that unless you're just looking at a particular channel? Like I'm used to looking at all three at once, so that's kind of where it just seems odd to flip it.
But the machine wants to look at those things that are correlated together all together. So if you have limited RAM on your GPU, you can only fit a few channels of a few images, then it'd be better to get one channel at a time rather than getting one row, for instance, of a image or whatever. So it could be, memory optimization reasons why you have a particular shape.
Okay. But
Yeah.
Go ahead, Ted.
So I was actually thinking about this, and just full disclosure, I'm not an expert on this, but if you have your whole image in memory, if say you're doing a bunch of operations like 256 convolutions, and those are operating across height and width, but within a single channel, then you would tend to prefer to have that memory as contiguous and as compact as possible. And so you'd want height and width in your last two dimensions. Now, sometimes you're going to do operations across channels, okay? And if that was the most common operation, then you would want channel to be your last dimension, because then things would be most contiguous. But it seems to me that in a typical CNN, you're doing way more within channel math and an occasional pooling across channels. And so you can optimize that compact, more contiguous memory access.
Perfect.
And to try to rephrase what you were saying, like it's the nature that if I'm going to look at stuff from a red, or if I have to compare things, I'm going to compare red and red between two different levels rather than comparing red and green between two different levels. It's that you're looking for stuff that's similar, right?
Well, so let's say you're doing I don't know if you know like CNNs, we're going to get to that, but let's say you're applying a 3x3 filter, okay? And if you do it within a channel, then you're going to have, within one row, 3 adjacent columns, and then you're going to have the row below and then the row 2 below that. And that'll give you a little 3x3 square, okay?
Mm-hmm.
If you have channels first and height and width as your last dimensions, then you're going to have 3 contiguous axes, and then the row below it is going to be separated. So if you have a 64 by 64 image, then it's going to be 64 later, and then the next row is going to be 128 later, but you'll have at least 3 contiguous axes. And then if you're going to do a lot of these 3x3s, you might be able to optimize sort of loading a contiguous chunk and kind of like, sort of iterating over that. If you had height, width, and channels last, then this little 3x3 filter, it would be accessing every 3rd memory spot in the row. And then it would be accessing, what did I say, 64? I don't remember what I said, but then it would be accessing 180 memory spots away to get to the next row. And so it's going to be more spread out. You're going to have less ability to sort of pipeline and optimize that memory access. So it seems to me that that perhaps, if you know sort of like what's the most common access pattern, that you want sort of the most frequently accessed things in your latermost dimensions.
It's a useful optimization, but you can actually store it either way. And if you go into, I believe you can do it in PyTorch. I know you can do it in TensorFlow. You can just tell it channels first or channels last, and it will know to do the convolution in a specific way. And over time, people have started preferring the channels first because of some hardware optimization, like Ted was just explaining. But at least in my experience, it also depends on the architecture, how many layers of convolution you're doing and all kinds of stuff like that. So I've seen benchmarks that have shown, okay, channels first is actually significantly better, but I've also had many cases of my own where it's like, it doesn't seem to really make any difference. So I would say it's not the hugest deal. It's just an additional note. someone had a question about normalizing by standard deviation versus normalizing divided by 255. So part of that, it doesn't really make a difference. You're just doing a simple linear scaling either way, because the way you would typically apply it is you learn the statistics. So for example, if you just divide by 255, you just are always going to divide by 255. And if you are doing the subtract the mean and divide by the standard deviation, you compute the mean and the standard deviation for the entire training set, for example, and then you just apply that mean and standard deviation on all images in the future. So if you're applying it to unseen images, you don't change that at any point. And at that point, it's kind of just the same thing as dividing by 255. It's just a different scaling factor and centering it around 0. So there's not really functionally that big of a difference. The important thing, though, is a lot of people use pre-trained networks that had some underlying assumption. They were divided by 255, or they used some specific scaling factor. So you need to make sure that you're matching that. And so in Torch Vision, they give you a pre-processed function that basically says, okay, I'm going to take your inputs and push it to the correct format, the correct scaling. And in terms of, I think the question in terms of performance was in regard to like channels first versus channels last. There shouldn't be any difference in terms of accuracy at all. But there will be potentially a difference in speed, but it might not be a massive one. So we can take a look at the code. They imported NumPy, they imported PyTorch. That's all pretty standard. They loaded in the image with the image IO, imread, and then they gave the path. And then we can see that the original format is 720 by 1280 by 3. So we assume this is probably height, width channels. And then they load this into Torch. So they say we have a NumPy array, we want it to be a Torch tensor. And then they permute the dimensions like we were talking about. So I'd have to double check on this, but I'm pretty sure my understanding of the permute function is you're saying you want the second dimension first, and then the 0th dimension second, and the first dimension last.
Yeah, the arguments to permute, if you supply them all, have to always be 0 through n-1.
Mm-hmm. Yeah. And then this is them showing the defining a batch of inputs. So they set the batch size to 3, and so what that means is they have the first dimension is the number of batches, or the size of the batch, and then this is the channels, and then width and height, or height and width, whatever direction that is. And then what they're doing here is they have a folder with a bunch of cats, and they're saying, okay, we're going to iterate through all of the cat files, and then we're going to load the image, we're going to turn it into a tensor, we're going to permute the dimensions, and then I added a piece to print the shape because I was confused what this line was doing. And apparently it's nothing, because they're just grabbing all 3 channels and just loading that in still. But if we run that, we can see that they're loading up the batch, and then I'm just printing off the shape, comparing before and after that command, and I saw that there was no difference.
Yeah, I think there was a comment in the book, Ryan, that sometimes there's a 4th channel, like for alpha or for other stuff, and they just wanted to strip if there were any extra channels.
Mm-hmm. Yeah.
Yep, it was.
And then beyond that, they're just showing that we can turn the batch into a float. We can divide it by 255. So this is an important point. Typically, the most efficient way to store the images with that 0 to 255 is to have it stored as a unsigned integer with 8 precision. Uint 8 is the NumPy data type. And so if you try to do some of these operations, like if you divide by 255, then what will happen is you don't have enough precision to actually make those floating point values. So 128, for example, should be around 0.5, but you don't have the precision to do that because the numbers available to you are only 0, 1, 2, 3, 4, all the way up to 255. And so you actually have to make sure that it's a floating point. So you actually have that 0 to 1 is a meaningful number. So you can represent it as 0.3, whatever. So just a small point to add there. And then they're showing the mean and the standard deviation. That's kind of just all the same stuff, just showing you can scale in that way. Any questions regarding the code on this stuff?
Can't you use the usual NumPy scaling? Because it, it saves means on its own and standard deviations in the object.
I'm not familiar with that. It's possible. I don't know. You said NumPy?
Oh, sorry, scikit-learn.
Yeah. So that's an option too. Yeah, and it will keep track of all of that for you. So one that definitely works. One difficulty is the if you want to normalize each channel specifically, then you might have to do something special with that. And then the other thing is it requires you to have everything all in memory at once, I believe, which isn't always possible with images. If you have a million images and they're a decent size, then you might not be able to fit everything in memory at once. And so what some people have to do is you iterate through all of your images, and while you're going, you're kind of accumulating a mean and standard deviation. But for the most part, scikit-learn should work fine. There's just some scenarios where you might not be able to do that. Any other questions in that regard?
I noticed in the code, you use the standard deviation, but I think in the code that they had in the book, they used the variance, which I wasn't sure if there was a reason for that or if that was just outdated, or because they used the variance for the normalization, then they square root it. And I was like, why didn't they just factor the standard deviation?
Yeah, I saw that too. I wasn't sure about that. I don't think there's any reason that they intentionally did that.
Standard deviation is already when we take the square root. When we don't take square root, it is called variance. And it is a common mistake with statistics, with the statistic concepts.
Yeah, that's what I remember too.
Yeah, I agree, which is weird that they calculated the same thing rather than just do the calculation itself. I wasn't sure if there was maybe some sort of weird optimization if you do it by calculating the variance and then doing the square root yourself. Maybe the library wasn't, but if no one knows, that's fine. It might be just something peculiar that they did.
Am I audible to you guys? Hello?
Yeah.
Yeah, so regarding what he said before, I'm not sure about it, but I think he might have taken the under root so that it becomes positive, and that way so standard deviation can be negative, right? So taking variance and then square rooting could remove the negative sign.
No, standard deviation is never negative, yeah. Because when we compute variance, it is sum of squares, and when we take square root, we always assume that this square root is positive. Classical, I mean, usual arithmetic square root is positive.
Sorry.
That's fine.
I did see what you were saying, Tommy. I don't remember where it was, though. Because in the book example on this one, I'm seeing the same thing. I did see them do the variance and then square root it at some point, though. I'm not sure why they did that. So moving on to 3D images, this is kind of just a step further from the other images. We're adding an additional dimension. So in the example they showed, I think it wasn't really the best representation of that, because what they did is they replaced the channels with the depth in the code example, but it's entirely possible that you also have multiple channels on top of depth. And so you might end up with a format where you have channels, depth, and then height and width. And so if you ever run across data like that, you don't really have to do anything too special in terms of representation. You just say add an additional axis, and now we'll load in the depth as well as the channels and height and width. It's not really anything too magic or complicated. So kind of similar path. They load NumPy and Torch, and then they load in, and instead of using imread, they use volread, and they say, here's where all of the images are. It's in DICOM format. Here's the shape that we get out of it. So we have 99 slices of the image, and then it's 512 by 512. And then they're pulling it from NumPy to a Torch tensor, making it a float, and then they're unsqueezing it so they can make it a batch. So you need your batch dimension even if you just have one. So then it's just a single batch, and then 99 by 512 by 512. And then they show that we can visualize random slices of this. And that's really all there is to the volumetric stuff.
I was curious if anyone had a background, I guess, in training volumetric models, you know, so like if they're trying, are they trying to find, like, let's say cancer somewhere in the body? If that was done, is that a typical model that you might find with that?
Mm-hmm. Yeah, that's one of the use cases. That's a lot of the time they're looking at cancer and tumors and all kinds of stuff like that. There's been a lot of Kaggle competitions that have been focused on that stuff. And in terms of modeling, it's not very much different. So we might normally have a 2D CNN across a 2D image, and then we might go to a 3D convolution. So you're just adding that additional depth. I've also seen people do 2D convolutions, and then it extracts the information out of it, and then they do like an LSTM or something like that across the depth. There's multiple different ways to do that. And another thing to kind of think about is another option rather than having depth is when you have video. That's exactly the same thing, where successive frames can be stacked up like that. And then you're looking across time rather than across depth. So if you ever play with video, that's exactly how you handle video too.
Well, so my question with that then is for the labeling, is that done per the depth channel? Like, you know, channel 5 has the cancer cell, or in the time video, or the video dealing with time, like at time this, which would be considered, I guess, the depth. Is that how that works?
Well, you can do lots of different problems with it. You can just do simple classification if you want. You can say, does this person have cancer or not? So that's one avenue. Or you can say, you can do some sort of segmentation thing where you're saying, here's specifically where the cancerous cells are. Or you can, like in self-driving cars, you have a stream of video. You're trying to segment out where cars are moving and stuff like that. So you're drawing a bounding box around things and keeping that over time. There's lots of different tasks that you can build out of that kind of data. It really just depends on what you want. That stuff is fairly difficult, though. Moving on to tabular data, I guess. So images are interesting, but they're honestly not as common as tabular data. Tabular data is going to be probably 90+% of what most people actually interact with. This is all of your spreadsheets and your databases and your everything like that. And so it seems pretty easy because stuff typically already comes in rows and columns, but sometimes it's not as simple as that because it might be storing a string, it might be storing missing values, it might be storing categoricals that need to be transformed in some way. So you have to think about your tabular data a little bit more than just saying plug this directly into a neural network. And so the three kinds of data that they were looking at was continuous, ordinal, and categorical. And so continuous is kind of just your standard numerical stuff where you're saying the temperature is 70 degrees out and there's this amount of wind and there's whatever other factors going on. But the magnitude actually matters. So there's ordering to it. And the magnitude of difference matters. So if you're saying it's 50 degrees out and it was 70 degrees yesterday and it was 90 degrees the day before, those are equidistant apart, and that actually is meaningful in some way. Whereas you can have an ordinal, some people might also do this categorically, but you might have like small, medium, and large, and you might just encode that as 1, 2, 3. But a large is actually 2 times as big as a medium or something like that. So it doesn't necessarily have a standard scale. It's just whatever the numbers are assigned to. And then you can have something that's just a true categorical where you're saying these aren't on any sort of scale. They're just kind of unrelated. So the example they used was you could have 1 for water, 2 for coffee, 3 for milk. And you're not saying that water is closer to coffee than it is to milk. That's not a continuous scale. You don't want to be showing that representation. So you have to separate it out in some way. And so the way that they described it is using one hot encoding. And so the way they showed to do it is using the dot scatter. And that's basically just expanding it out to a one hot encoding. So they show, this is where they showed the variance thing, I guess. So they were talking about you can scale your variables with the mean and the variance, and you can use that for normalization and all kinds of different things if you just want to gather statistics and stuff. And then they also showed in the wine example, they were showing that you might want to filter based on various different things. So you can say, I want all of the rows where some certain variable is greater than 3. And so you basically say, grab that axes, say all of the columns where it's greater than 3, and then it will return you a list of trues and falses basically, and then you apply that to your array, and all of the ones that are true will be returned and all of the ones that are false will be left behind. And so it will return an array for you, showing some new data that's been filtered in that way using the Boolean indexing.
So guys, I've got a quick question. In your experience, when you're working with things like that are tabular data, in the past, I've used pandas rather than NumPy. I mean, in general, what's people's experience? Do they, once it's more sort of tabular data or database data, is it easier to work in pandas, easier to work in NumPy? I haven't worked too much in NumPy.
Pandas.
Yeah, the standard is really pandas. They actually said in the chapter that they just didn't want to introduce an additional library that people had to learn in this. So they just use NumPy and the inbuilt CSV module in Python, but everyone uses pandas. It's really just a standard.
Yeah.
NumPy is more efficient when you have huge data. You can look at the internet NumPy within Panda, and there are a lot of examples about it. So when your data is not huge, Panda is fine, and it is more, more user-oriented than NumPy.
Yeah. Okay, thanks, Brian.
Well, I was going to say on that note too, just because now I've been having to deal with working with very large data frames, that there's other libraries that adhere more to, like the data framing format of having your columns named and things like that, because NumPy is just purely numbers. I don't know how to say the library VAEX, but that's meant to deal with like millions or billions of rows in an efficient precompiled method. And that's kind of their thing. So they're like, if you're finding efficiency problems with pandas, use their library.
Yeah, I was going to comment that for me, like pandas is how you play with it and you do EDA and you do stuff. If it fits, if you can, handle it. But it's not like you actually do computations. Like my understanding is scikit-learn is basically turning everything in pandas into NumPy behind the scenes before it actually does any math.
Mm-hmm. Yeah.
Yeah, it doesn't even have to do any conversion. So all pandas objects are NumPy objects under the hood, and so they just transparently expose those APIs to scikit-learn.
So looking at the code examples they gave to us, this is following along with the tabular data. They gave us this file with some wine data. It's in CSV format. Like we were just talking about, you might load this in with pandas or some other format, but they showed that you can load it in with NumPy, give it some different arguments, and then you load it in the NumPy array. And then I wouldn't really worry too much about this stuff. It's all just loading in the files. And then they've actually got their array with their data and their column names. And then they take the NumPy array with the data and they turn it into a tensor like we've done a few times now. And then they print out the shape and the data type. So we can see that it's this many rows, this many feature columns. These are all of these. And then they're showing that they're storing it all as a flip32. And so what they're doing here is they're wanting to grab the data and then the target. And so split those into two different NumPy arrays or torch tensors. So what they're doing is they're saying grab everything except for the last column, and then grab specifically the last column because that's the target. And then what they're doing is they're showing that process of one hot encoding the target using scatter. So they're basically defining the array. So they're making it the size is the number of rows, and then this is the number of possible qualities. It probably would have been good if they defined that in some other way rather than just defining it as 10. And then they're doing this scatter operation, which I don't entirely understand. I haven't looked at this in too much depth. I know that it's doing the expansion of this target into the one hot encoding, but I'd have to look at what the 1 and the 1.0 arguments are actually doing. I've typically done one hot encoding prior to making the tensors. I haven't done that operation in PyTorch very much.
So Ryan, I can actually comment on that because I was just thinking about saying something. So if you scroll up just a tiny bit where they pull out the data and the target, one thing that you may not notice right away is that the data is two-dimensional. When they pull out the target, they're actually just pulling out a one-dimensional vector. It's not an array. So down below, what they do is they actually unsqueeze target in order to turn it back into a two-dimensional array. It's still, you know, by one, but it is two-dimensional. And so then basically we're going to start with a two-dimensional thing of all zeros, and then we're going to have a two-dimensional with the values of whatever 1 through 10 or whatever it is. And so then we're gonna, thanks Ryan, that's actually good, yeah. And then we're gonna plop ones. We're gonna plop the 1.0s that you see on your last parameter into the column that corresponds. So it's treating the target as a indexer instead of as sort of numeric data.
Mm-hmm. So this is saying what value to actually plug in. So I could, in theory, change this to like 5 or something like that, and it would plug in a different value than the standard one hot encoding.
Yeah, and I'm trying to remember. I can't remember specifically. There was some time when I wanted to like blast zeros into something, like it actually had non-zero values, and I wanted to overwrite some of them with zeros, and I can't remember why now. But I guess you could also use it that way if you just wanted to zero out sections.
Yeah, okay. That makes sense.
I had a quick question with PyTorch. I mean, I know it's less efficient to dynamically allocate arrays like what lists do, but does Torch, you have to predefine the arrays before you can actually put actual values into it, like what they're doing with the target one, torch.zeros, then doing the scatter part? Is it not able to dynamically allocate new objects?
If I recall correctly, it's got two options. You can either operate on an existing one in place, or you can create a new pointer to existing storage, right? Those are kind of like your two options. That's the difference between like scatter and scatter underscore. So that always implies that there is something there that you're sourcing. Scatter is kind of an operation you could argue it should create if it doesn't exist, but I think just from a consistency of API across the board, they say you have to have some memory already allocated that I can do something with. You either copy it or just overwrite it. The API very much looked like it was built from that approach.
Yeah.
Yeah, and in this particular case, I'm not quite sure what would happen if you didn't do the in-place scatter, because we have zeros in all the places where we're not blasting ones, but scatter wouldn't know that, right? There's not an argument that says if not one, then put a zero in there.
Yeah.
So it does seem to me that even if scatter could do that, it would be writing all these zeros, whereas it's a lot faster to call zeros and have it all be zero initialized in one fell swoop and then blast in the ones.
And I think there's also something with like, you can have different types of underlying storage implementation. Like there's the sparse arrays that you can do. And so you don't want to try to, like, especially for one hot, you want it in place because you're playing with that sparse array. But even if you're not, I don't think you want to do any kind of other operations, because then you'll hydrate it and whatnot. That just get weird.
Great, thank you.
So this is showing the unsqueeze operation, just adding that additional dimension. That's what we just looked at right here. So it starts at 4898. It's just a single dimension, and then we're adding on an additional dimension. And then this is the portion where they're calculating the mean. You just do torch.mean, and then the tensor that you're interested in, and then the axes that you want to calculate the mean across. And then same thing for the variance or standard deviation like we saw in the previous one. And then they show that we can normalize using those. So you subtract the mean, and then you take the square root of the variance like we just had the conversation about. And then this is where they do the indexing that we were talking about. So they're looking for the rows where the target is less than or equal to 3. So all of the times where the quality of the wine was less than 3, grab all of those rows, and then we can look at the characteristics of that and see what's special about bad wines. And then they split it into various different sections. So all of the wines under 3, greater than 3 but less than 7, greater than or equal to 7. And then they can measure the mean values of all of the different variables and look at that also across the bad group, the medium group, and the good group. And they can see which variables actually have some shift across the quality of the wine. And so the key concept here beyond just the wine data is actually we've got this data and we are selecting the rows where the target is less than or equal to 3. And so just understanding what this actually looks like. I don't remember which code I've run. I'm hoping I've run the right stuff. And so what this does when you do this comparison is it's just checking each row, is this less than or equal to 3? If that's not true, it puts false. If it is true, it puts true. And then when you're looking at your data, what it does is it grabs all of the ones that are marked true, it will return. All of the ones that it marks false, it will just discard, basically. So we end up with various different sizes of bad data, mid data, and good data based on the number of rows that were returned true by this condition. This is the same as NumPy indexing, if you're familiar with that. It's just in PyTorch now. And then they showed that they set some threshold for sulfur. So they said, this is some significant difference between a bad wine and a medium wine. So let's use that cutoff point, and anything less than this, we're going to mark as a bad wine. So they use this torch dot less than. And so they're saying, look at the sulfur data and then look for anything below this sulfur threshold. And then that tells you the indexes of all of the potentially bad wine. And then they just kind of continue on with that comparison. And then they just do some calculation in terms of like how many they actually got of the bad wines versus the total. And he should probably stop there. Does anyone have any questions in regards to that stuff? So moving on to time series data, this is a pretty common use case. Rather than just having wine, you might have something that goes over time. So you're recording records every single day in regards to something. And you want to keep that time series nature of it where like the ordering of the stuff actually matters. And so this is kind of a technical area, so I don't know that we need to go into it in too much depth until we learn more about this stuff later. But basically you can expand out tabular data. So when you think about a normal spreadsheet, it's got its rows, it's got its columns, but then when you have time, you might want to add an additional axis where you say, okay, here's how things are changing over time. And so the way they showed to do this was you can change the data so that now you have 3 dimensions rather than just 2. And this is kind of hard to visualize as a spreadsheet, but in terms of a NumPy array, it looks, hopefully they have a visualization. It looks something like this, where it's sort of like the 3D array that we were looking at with the images. You just have a time axis. So the first one is across hours, and then this is across features, and then this axis over here would be across days. So that's how you can think of it. And so all we're doing here is we're reshaping the data. So it's as many days as we have. When you do -1, it just basically expands it out for as many points are left over. And then we know there's 24 hours in a day, and then however many features you have. In this case, I think we had like 12 or something like that. So basically it's just doing a reshape on the data. In this case, it's a view of the data, just saying, I want this stride and this sort of organization of the data. And on top of that, they were showing that we can also do the hot encoding and all of the other pre-processing stuff that we were doing, and then we can concatenate that. So if you have two separate tensors and you want to stick them together, then you can do torch.cat and it will piece them together for you. Ted and I were actually having a conversation about, I don't know that that was the best way to show that concept, because they didn't really motivate why you would organize the data in that way. Maybe we'll find out later on when they show us that data used in a model. But I would, at this point, the takeaway is just you can reshape the data into a time series format. Looking at the code, same thing, importing NumPy and Torch. These two basically always go together. And then they're loading in the bike sharing data set using NumPy, and then they're turning it into a Torch tensor. They're looking at the shape, they're looking at the standard stride, and then they're doing that view operation that we were talking about. And you can see that the shape has changed from this to this. So this is the number of days of data that they have. This is the number of hours, and this is the number of features. And then we can see that the stride was originally 17 by 1, and now it's changed to 408 by 1 by 17. And that's some crazy thing that's used to just manipulate it into the right shape that we're interested in. And then they show that they're doing that same hot encoding operation on the weather, and then they're showing that we can concatenate those together. So we've got our bikes data, we want to concatenate it to the weather data, and that's really all they're showing there of interest. Any questions?
Hey, just as a random side comment, like if I ever was rusty using colons and slicing things on the left and on the right with colons, like by the end of this book, I am clear I am no longer going to be rusty.
Yeah.
I know you did that
question in the chat, I think.
Oh, sorry.
If something happens on the hour at 8 a.m. or every few days, it would make sense to align hours and days to find features with convolutions. Yeah, so there's actually a lot of different things that you can do with this. There's different ways that you can aggregate across days or across time. They didn't go in very much depth. A lot of the times we would look at autocorrelations and see which features are actually important, because the 24 hours ago feature might be very important, or 12 hours ago, or whatever. So you can look at the autocorrelations and you can see which features are actually useful. The way that they organize the data in 24-hour batches, and then also across the days, we'd have to see what they're planning on doing with it, because there's plenty of other ways that they could have formatted that data. And it just depends on how they're actually going to plug it into the model. It might be a useful way to use it. I typically wouldn't organize it like that, but I'd have to see what they're doing.
So if you've used pandas, and kind of along the theme of some of the other questions, if you've used pandas and date time indexes and resampling to create those groupings by dates, then you can also read that in, right? And then kind of manipulate it into these structures, or is it because it's a little bit more intuitive to do it through those tools rather than taking it, taking these tools to do that? Any thoughts there in terms of just reading in some of that date time series data?
It definitely makes sense to use the Panda stuff when it's available. I would say that PyTorch is not really where I would do the data munging stuff. It just doesn't have all of the stuff that is really what you want in terms of time series. You kind of have to massage it a little bit outside of PyTorch and then feed it in later. So yeah, resampling and all of the various different rolling aggregations and stuff like that, you probably want to do in Pandas. You can do them in PyTorch, but it's probably going to be a little bit extra work because Pandas already has all that stuff built in.
In my experience, when I've dealt with time series, and we're sort of maybe going slightly on a little bit of a tangent here, but I've usually done sliding windows, right? So this is a very simplistic approach of you just take a 24-hour period and chunk it up by 24 hours. But in real world problems that I've played with, at least, you actually do sliding windows and you say, okay, I'm going to do it for every hour and I'll create a window and just move the window along 1 hour at a time, right? Across as many days as I have. Because it may be the accumulation of all, what happened the preceding 24 hours or 12 hours before this hour that's important kind of thing, sort of thing. And so that's just something to throw out there. In the real world, that's how I've done stuff.
Yeah, you can have some sort of history and you say, I'm going to look at the last 36 rows or something like that. And you just roll that forward every single time. So you're always looking at 36 rows of history or something like that.
Yeah. I think, and this is one of the things that kind of like it was caused me a lot of thought. One of the things that we think of when we were talking about how to represent the data, a lot of it to me felt like, oh, how do I take, data values and then represent them into the array, right? So like, how do I convert categorical data into array items? Okay. This one is kind of where it got to the point, and it's kind of building on the channels discussion, right? Of what does the actual structure and organization of the array can have computational meaning, but it also has, data meaning from the standpoint of, I have, a tensor, which on one dimension is the hour of the day, but I'm going to process that entire day together, which means I can look for a correlation between the hours, right? Most of the time we're saying, hey, is this data point over here anyway related to this data point over here? And here we have a built-in, they are definitely related, and you can actually use that to help, determine an outcome, because all of those data points are in your model at the same time, versus taking each data point and throwing it through your model and seeing if there's some kind of connection to them. And that's why I thought this was a really interesting play on that, because to Stephen's point, this is creating those 24-hour windows, but it's doing only, it's doing that every 24 hours. If you want a rolling window, you can construct the same thing. You do it every hour instead of every 24 hours. So it really is as you're thinking about, the tensor itself, the tensor has to express the full set of data that you want to throw through the model at one time, rather than a bunch of different data points that are each thrown independently. So there's a assumption of mutual exclusivity, or are these what we consider to be separate data points, are they really connected data points in a larger data point? And it's just it really got me thinking as I was going through this part. So
Yeah.
I don't know if that helps.
There's a lot of different things that you can do with time series. Every time I play with it, I end up getting a headache because there's just a lot of different ways that you can organize the data and pre-process everything. The way that I've typically ended up doing things is not doing a reshape like they do, where they're saying, okay, here's our days, here's our time. I would leave the days out of it, and I would just have running hours, just moving through time. And then when I want to prepare a batch of data for training, I would just say, I'm going to grab random 24-hour chunks, not necessarily line them up on the days, but maybe there is some reason why you want specifically to organize in days, because then your inputs would be, this is always hour 0, this is always hour 1, and stuff like that. There's just a lot of different things you can do there. So you have to kind of understand your problem and pick at the details a bit.
So if I could just comment briefly, you know, I'm not overly worried that the way they're showing to set up the tensors in this chapter is exactly the way you should or always or definitely will later in the book. I think the takeaway from this chapter is getting really comfortable that whatever data we have, since this is a PyTorch book, we're going to put it in a tensor, and oh look, tensors can have different shapes. They can be 1-dimensional, 2, and you know, like for that CAT scan thing, we got up to I think it was 5 dimensions, right?
Mm-hmm. Yeah, I think that's a good point. It's not really a focus on time series stuff. They were just looking for an example to say, here's how you use view, here's how you reshape some data. I think that that's the key thing, is just learning that operation exists.
I just wanna add to, isn't it that it's possible that you're not only just gonna use a days, you can actually group them, like 5 days, 24 days, 9. So you can like do an inception. So the concept maybe is you're doing some form of a grouping, but you can group it now with different group of days. So you can stack them up like the CNN is. So by doing that, you can group it now by other, maybe there's a 5-day work, 5-day where works, but we can also want the 10 days and then the 24 days, and we can together, maybe there's a relationship there, something like that, right? Does that make sense?
Yeah, that's another possibility. Time to move on to text, unless there's any additional questions. So representing text, this is another area that's pretty hot, similar to images. People have had good success with RNNs and transformers, and we have access to all of this text data on the web now. So people have built these really massive models that can do all of these interesting things, like GPT-3. I think we looked at that probably first or second week, something like that. And so the struggle here is we need some way to take our words and our strings and turn them into something useful numerically. And so there's a lot of different ways that you can encode these. Some of them are useful, some of them are not that useful. So for example, if you took the index for all of the different characters, so you just said A is 1, B is 2, etc., that's not very useful because it doesn't really encode very much information for you, and it's telling you that A is closer to B than it is to T, and there's no real reason to show that. And so they showed that you can one-hot encode all the different characters. So instead of implying that ordinal relationship, you can just one-hot encode them, but then you blow up your data size by the number of unique characters that you have. So if you have alphanumeric, then it's A through Z and then 0 through 9. That's plenty of different options, but then you can even go beyond that, where you have all of the different special characters and emojis and all kinds of random stuff. So you can end up with very big data by just trying to encode every single character. And you still probably won't have that useful of information because you're just telling what each successive character is. And so another approach that is more useful is actually one-hot encoding each of the words. So you're saying aardvark's the first word in your dictionary, so you give it the index 1, and then you one-hot encode that, and then you stack a bunch of those forward. So you build out your whole sentence from one-hot encoded words. But that's still not generally what people use because that explodes out to the size of your vocabulary. So if you have 30,000 unique words and you have 30,000 across one dimension, and then you have the number of words in the sentence across the other dimension, then you can just take some small amount of text and then completely blow up your memory because you just are storing so much so inefficiently. And so an in-between approach, rather than just taking entire words and one-hot encoding them, or taking individual characters and one-hot encoding them, is byte pair encoding, where they do some look at the statistics of the text and then they figure out what are the useful groupings of characters. So you might have ology and bio and various different root words that are useful, and you can learn something from those specific root words and apply it across everything. And that will share more meaning than each word, because if you think about it, you'd have to learn, so like you have biology and biological, you would have to learn those meanings entirely separately. But if you're using the subword pieces, then you're actually learning something about the core concepts and then piecing them together. So you can share some knowledge in that way. And then in the final section, they don't really talk about it too much. They don't say the full details of it, but most people don't actually do one-hot encodings. They use these embeddings, and what the embeddings do is it maps it down to a smaller space. So you have a dense representation rather than 1, 0, 0, 0, 0, 0. You have some set of floating point numbers that map out where similar words lie. And there's various different ways to generate and train embeddings, and that's kind of beyond the scope of what we're learning here. Maybe we'll look at it later. But the general premise of it is you're figuring out what words occur in which context. So you know that ball ends up in the same context as kid and sports and various other things, and you look across big bodies of text and then you figure out exactly what words the word occurs along with, and then you can figure out some understanding of that just from the context. And then you can end up with something that's 100, a dimension of 100 instead of 10,000 plus when you do the one-hot encoding. So they didn't show too much detail about the text, but that's how people typically handle it. Any questions in that regard before I go through the code?
So yeah, probably a slightly naive question from me, but so TD-IDF is a type of embedding, right? Or am I mistaken in thinking that?
In a sense, so that's just purely looking at the word
Frequency
counts. Yeah.
Yep.
Yeah.
Yep.
So that's people wouldn't typically call that an embedding, but it is a way to represent the text in some sort of vector. Right. The embeddings are different in that they're the key factor is that they're much denser. TF-IDF can still be 30,000 wide because it's the number of unique words that you have, and then the embeddings are much smaller because you're mapping it down to an embedding space.
But at the general level, I mean, they're both a way of mapping from one space to another space, right? The embedding being a more compact, dense space, but even TF-IDF is a way of mapping, you know.
But that's what the word embedding means, though, is bringing down a high dimensional space, because you're basically having the raw bag of words dimensionality in the TF-IDF vector.
Yep. Okay. Good point. Thank you.
Yep. So then same as before, NumPy, PyTorch, they're loading in a text file, they're splitting it on the lines, and they're grabbing specifically line 200, and this is what the text looks like. And then what they're doing is they're defining a torch tensor. It's filled with zeros now. They're making it of the size of the line and then the number of characters that they're interested in. So they're doing alphanumeric plus some other characters. And then they are iterating through the text, character by character, and then they are looking at the ordinal values. So that's the A is 1, B is 2, C is 3, etc. So they're doing a check saying if it's less than 128, then we'll give its actual value. If not, we'll just give it a 0. And they're assigning this to this torch tensor that they just allocated. And then they're doing some basic text cleaning. They're removing punctuation and they're lowercasing it, and they are replacing the new lines with blank space, and then they're splitting it. So now it's a list of the individual words rather than the raw string. And then they're building out this mapping of the vocabulary. So they've created a vocabulary out of the long document, and then they have to build a index lookup. So they're basically saying, I want this word to map to this specific number. So they look at their dictionary, they see that there's 7,261 words in their dictionary that they've created. And then they want to look up what's the index for the word impossible. And then it turns out that it's 3,394. And then they do that same thing over here. They're doing similar to what we did with the characters in the first one, where they're iterating through each word, they're finding the index for that word, and then they're assigning that index to a 1 in their one hot array. And then when they're printing this off, you can see the indexes of all of the different words. So impossible, we just saw as 3,394, and then Mr. is this number, and Bennett is this number. And then when we're looking at the actual size of the array, this is 11 words in our string that we're looking at, and then it's 7,261, which was the size of our vocabulary up here, the size of our dictionary. They're doing the unsqueeze operation to add the additional dimension. And then this is just looking through the set of characters that we have, basically. Any questions on any of this stuff?
I'm not sure if I missed it, but like, what was the benefit of having all of the characters sorted at the end there?
I don't entirely know what they're trying to show here. I think they're just showing they're showing these in alphabetical order, and then they're showing what this maps to in terms of the index. Why they want to show that, I'm not entirely sure. So they're just showing A, B, C, D. They're counting up through these, and then it goes to
there was an earlier comment that the curly quotes were above 128. Maybe that's just to show you, like, oh, by the way, this is why we had to do the less than 128 thing. I don't know.
Exactly. So any Unicode character, so that's the ASCII decimal representation of a character, and that number that you're seeing there. And so For a Unicode character, it's well above 128.
Oh, okay. So it's just limiting the characters that it's considering as part of the model, the vocabulary, anything below 128, which is covering all of the letters in the alphabet and then like relevant punctuation that is found in the text.
You got it.
Okay.
It's ASCII. That's a common filter that's done on a lot of databases and a lot of text files, just to limit it to ASCII, to avoid, you know, like E's with accents on them and all of the other Unicode characters that pop up in databases.
Hey, so random question: are emojis part of Unicode now?
Yeah.
Well, I didn't know that. That's news.
I mean, basically, it's they have a Unicode representation, and it just happens if you find it that replaces it with the visual for the emoji. But yeah, there's a specific, as if I remember right, there's a specific emoji sub working group inside of the Unicode working group.
Wow.
That does the the allocations.
Yeah, I think you're correct. And then I think for like skin tags, it's kind of like an add-on to that code.
Wow.
Yeah, so like maybe a smiley face is a Unicode character, but like dancing parrot isn't.
Correct. Well, and so there are some extensions I can't remember for like localized Unicode, but then there's also the smiley face. There is a Unicode string, you know, pound ABCD that represents smiley face. How a given environment decides to represent that is up to the environment. They're not always, that part's not uniform, but it's just this is the international character, or this is the number for the international character for smiley face.
There's a lot of other situations more mundane where that happens, where there are 2 or 3 or many representations of a given character, like the E with the accent. You can use the embellishment, you know, accent character to extend a Unicode character, or you can use the built-in E with an accent.
I'm sorry I took us a field of machine learning, but I love it. This is so cool to know that Unicode has standard.
This is to the point of machine learning, especially if we're talking about text. This also has to do with sentiment analysis.
Indeed.
Yeah, like if you're doing tweets, like, you would absolutely want to understand these, right?
Yep.
You would want to normalize them to the same sequence of characters. That's all you'd want to do. So this quick and dirty, taking those quotes, for instance, and turning them into non-characters, it would be better if they turn them into quotes. There's a package for translating Unicode down into ASCII as best as possible that would have fixed that a little better.
Also, libraries that'll change the emoji into text data. I think it's called like the Emojify or something like that.
So yeah, you want to use those packages if you got emojis, so that you can get them into a common format, so that so that somebody who uses the text ASCII representation of a smiley face, they're given the same emotional content as somebody who used the Unicode character.
I think that's all we have in terms of the chapter. Does anyone have any closing questions or additional things they want to discuss, talk about? All right.
Well, if there aren't any other questions about this chapter of the book, let me get this out of the way now. So I already scheduled that we would do the next chapter, chapter 5 next week. It's about the same length, actually just a couple pages longer, and I would argue slightly meatier. So if we weren't going to do 2 chapters this week, I just assume we're certainly not going to do it next week. So so chapter 5 gets into learning and gets into sort of gradient descent. Hey, Ryan, you and I had a brief chat. I created a poll to see if the current people who are attending would have a preference between 2 p.m. and 12 p.m. the current time. So if you want, I can just kind of throw that up now.
Sure.
And just see.
Sure. Go for it.
All right. So we just wanted to check because we want this to be, you know, as convenient for people as possible. And so I tried to order the choices where you could say basically like, yeah, you know, I can make either, but I have a preference, or else you can say like, no, actually, I can only make one time or only make the other.
There's sample bias. You're surveying us before 2 o'clock.
Well, I figured better to sample close to, I don't know.
Yeah.
But yes, yes, there actually is a choice called I would come at 2 o'clock, but I can't come at 12. And I figured those people
Nobody's
won't
gonna
be
check
here to
that.
answer that way. So I didn't bother giving people that choice.
Does this have any reflection on the time for the second meeting?
Yeah, so actually Ryan and I discussed potentially just flip-flopping the two. So to us, we would still be here from 12 to 4, but it would be if people would rather do the project stuff first and then the book from 2 to 4.
So that one might have been a better question then. Wait, do you want to flip flop or do you not want to flip flop? And if you flip flopped, I'd be here both either way. You know, that kind of poll.
All right, let's see your poll, and then we'll tell you what you should have done.
All right, just
you can't win. At surveys always
exactly
subject to criticism.
I was just gonna say, isn't that the nature of polls? Is that you do them so that people can then criticize you?
No, you do them out of a true desire to know the data that you're trying to sample.
I was going to ask, we need Becky on her opinion on this.
Yeah.
She does polls, right?
I was going to say that welcome to my world on the point that you're doing this to invite criticism.
Strictly speaking, it is a biased sample we have here for people who vote, because they're already capable to come at 12 p.m. regular.
Yes, yes. Clearly, the people who would come at 2 but don't come at 12 are not represented. But at least the people who are here, it seems like most of them are flexible, but they like the current time. So.
Right, but the other thing to consider is, and maybe this is because we've been doing it, but I also noticed that far fewer people are on at 2 than are on at 12, right? So we're getting the majority of people by polling now.
Yeah. Okay, so on that note, I'm going to invite you to discuss polling or any other topic in breakouts.
You guys, it's next weekend or holiday weekend?
Actually,
yes.
I thought it was the weekend after.
It's the Monday after. It's the Monday that is 9 days from now is Labor Day.
Right. So yes, it's the very beginning of the holiday weekend. So if any of you have more of a life than I do and actually do things, and want to consider skipping a week, we can discuss that.
I thought this book club doesn't have holidays.
Maybe that's just this year.
Book club is the holiday.
I think that's part of COVID. I think nobody has holidays anymore.
Yeah. I kid, but I really don't have any Labor Day plans. So.
I don't either.
Okay, I'm gonna set up some breakout rooms here. All right, and I think I figured out how the breakouts work. So third time should be the charm, hopefully. Here you go.
What are the benefits of breakout rooms? What are we doing?
We're just hanging out and getting a more. Oh, I didn't realize Ryan was in this.
Meeting people.
Yeah, no, there's no real like intended direction. It's just when we used to meet in person, everyone was able to talk more freely, and now it's kind of just this more directed thing where only one person's able to talk at a time. Like before, it would be like we're just sitting at a table and nothing's going on. Everyone can just talk with who's next to them, and we're trying to give that a little bit.
Okay, cool.